to show that even sets with a technical length of 0 can still be corresponding to the real set 0 to 1, right? Now I want you to cut out the middle third. So 1/3 to 2/3, we just cut that out. It goes away. This is the first iteration of the Cantor set. Then we take each of these intervals and we cut the middle third out of them. 1/9, 2/9, 7/9, 8/9. And then, this is the second iteration. The third iteration, we cut out the middle third of each of these. 1/27, 2/27. Gets cut out. 1/9. Then we get 2/9. So this is 6/27, 7/27, 8/27, 1/3. And then you get the big gap in the middle, and it repeats. So then, C infinity, the limit of
0, right? Like this.
The limit of all these iterations is just a discrete number of points.
Oh, that's the number line.
No, because the number line includes every number. This
includes every number.
No, it doesn't.
Oh, but it's still infinite. It still has an infinite number of numbers.
How do you know that?
Because there's still an infinite number of points, discrete points, on this set.
Okay. Would you believe me if I told you we can associate a specific number? So, like, for example,
1-to-1 correspondence.
Yeah, with
this Cantor set
and the natural numbers.
Yes. Even though some of the numbers are missing.
Well, then you'd be completely wrong. Then.
Wait, what?
Okay. Would you believe me if I told you there was a 1-to-1 correspondence with the rationals? I mean, all of these are rational, right? So the limit should be rational as well, right?
Okay.
So would you believe me if I told you there's an association between A and B?
No.
Why?
Because some of the rationals are missing.
Okay. So do you believe that it is smaller than the
I think they're the same size.
Well, then you'd be also completely wrong.
No, because they're still both infinite. So how can you say?
Is it like one of those things like closed doesn't mean not open?
This is what we call a bijective relation. When we have infinite sets, we see which one is bigger by making a bijective relation between the two.
Like a 1-to-1 correspondence thing.
Yeah, like if I have 2 sheep and the farmer next to me has 3, we can make a 1-to-1 relationship and see that the farmer next to me has more, because there's an element of the set that I can't match up with. In the same way, we can show that the naturals and the rationals actually have the same number of elements, but the naturals and the reals don't have the same number of elements. So now, would you believe me if I told you the Cantor set has the same number of elements as the real numbers?
Yeah.
Good.
Why is that right?
Well, because essentially everything we do in the Cantor set can be described by a binary sequence. Every single number. So, like,
okay,
wait, what?
Okay, I'm listening.
So we can describe every single number by whether they go left or right in the first iteration, second iteration, and so on. So, for example, you might want to stay on the left here. This is left. This is right. This is left. This is right. This is left, left. This is left, right. This is right, left. This is right, right. And then this is left, left, left. Left, left, right. Left, right, left. Left, right, right. Right, left, left. And so on and so forth. And so you can describe left as a 0 and a right as a 1. And it turns out that any infinite binary sequence of numbers, the set of infinite binary sequences of numbers actually has a bijective relation to the reals.
And what is the application in real life? No application.
No, there's applications in topology, which in turn, topology has huge applications in manifolds and metric spaces, which is what forms the basis of relativity.